a spitball is launched at an angle of 42 degrees with an initial height of 2 feet at an initial velocity of 23 feet per second. Will it hit somebody 12 feet away? Is the first question. We'll call that question number 1. Second question is, how long until the spitball hits the ground? And then I added a third question last night because I want to teach you another function that we need today of what is the position of said spitball in relative to the person launching it after 0.8 seconds. Okay? So there's our 3 questions. First thing that we should do is we should come up with a parametric set of equations to define this scenario. Okay? So what would my x of t function be? X of t. What would my x of t function be? We'll all answer at once. What's my x of t function? What do you got? Go for it. 23 cosine of 42? And then? Need a variable in it. Times t. Yeah. Okay. What's my y of t function? Negative 16t squared. Markers and socks are in 216.
You ever watch Liar?
Mm-hmm.
When he gets that car back, I'm taking this.
Fine. Negative 16t squared. Plus 2. Okay? That's our functions. Graph them. Right? It's 42 degrees. Should just look on here. 42 degrees. Make sure your calculator is in degrees for this one. Otherwise, you're not going to have the correct answer. It's going to go backwards. Nobody wants a spitball that goes into their mouth. Oh, no. Oh. Okay, Yes? 12 feet away, there's a person. Well, let's put a person 12 feet away. We'll make them 6.28 feet tall. Does the spitball hit the person? Yeah, I would say so. Okay. Unless the person's sitting, then you might have launched it over the person's head. Right? Because if you're sitting, you're not 6 feet tall, you're probably only like 3 feet tall. So, gotta change that, change that perspective. Back. Okay? So I would say yes, we hit it. We hit the person. Okay? Question number 1, will we hit the person? Yes, we will. Okay. Question number 2, how long until the spitball hits the ground? Got 2 options here. We could trace that and try and get close and get a rough estimate guess as to it. Or what we can do is we can start a new function. In our new graph, the only thing that I care about is the verticalness of it, because I want to know when it hits the ground. So I'm going to go negative 16. Now my function was negative 16t squared, but this is a function of x. So I'm going to go negative 16x squared plus 23 sine of 42 times x plus 2. And when I do that, now we can analyze our graph. We can find the 0. We can also find the maximum height. And that then allows us to answer a couple of questions on this one. Oops. This one first. And And then lastly, the extra question that we have for this particular one, we're going to go back to the parametric function. You can go back to the parametric function by hitting Control and then to the left. That will allow you to go back to the parametric function if you have 2 different windows open. If you only have 1 window open, we're back on the parametric one. Okay? And now what we want to do is we want to trace this function, and we want to see what our position is at 0.8 seconds. So under menu, there is something called trace. And when you click on the trace, there's something called trace step. Trace step says how often it gives you a value on your function. Okay? trace just puts it wherever you want. Okay? So we're going to go into trace step because it defaults to automatic. Okay? I want to change that trace step to 0.1. We're going to go every 10th of a second. It's going to tell us the position of the spitball. Now, downfall, when I hit OK, it takes me all the way back out. So I got a retouch menu, retouch trace. This time I want to go wrap trace. So at 0 seconds, the spitball is still in the straw, and the person is getting ready to expel their air to launch said spitball. Then, here's the flight of the spitball. 1/10 of a second in, we're there. 2/10, it's there. 3/10, 4/10, 5/10, 6/10, 7/10. We're basically where we're hitting the person after about a little bit more than half of a second. 8/10 of a second is here is our position. Okay? So in answer to question number 3, what is the position relative to the launcher? The spitball is 13.67 feet away and 4.07 feet off the ground. And I got those numbers from right here. Trace function. It's going to come into play when we start writing a Ferris wheel later on. Okay. Everybody good with all of that? Fantastic. What I would like you to do now is, I would like you to have Christian Yelich hit a baseball, and you tell me if he clears the wall, if he hits a home run, or if he doesn't, and tell me the maximum height of that ball. Home run, not a home run. What do you got? I got a no home run. It's on the wall. Your wall not tall enough? My guess, after having gone through one class day, my guess is your wall is only 6.28 feet tall. Yep. Okay.
Oops, I forgot to. Capture the page first.
Okay. Question number 2 was, what is the maximum height of the ball? So now we can go into this one. And we can go negative 16x squared. This is going to be at 18 degrees. Oops, this was 3 feet. It's 150. Maximum height 36.57 feet. Yeah. Love it. Now, let's think back. Again, I know I'm making you think back way back. When we first started the unit circle, so what was that? September, end of September, beginning of October. Okay? We said way back then that any point on the unit circle has what for its coordinates? Any point on the unit circle has what for its coordinates? Any point that's on the unit circle, this point right here has these coordinates. It's another way. This point right here has these coordinates, but this point right here would have specific coordinates. What would those coordinates be? X comma Y, right? Right? But on the unit circle, they're not X comma Y, it's what? Cosine comma sine? It's cosine comma sine. So if I wanted to parametrically put a circle on my calculator, the x function would be x of t equals r times the cosine of t. The y function would be y of t equals r times the sine of t. We can graph any circle parametrically using that. Okay? So if I have a circle centered at the origin, with a radius of 30, what would the parametric equations be? X equals what? Of t? Gotta have a variable, right? Okay. So it'd be 30 cosine t. What would the y one be? 30 sines of t. But that's for a circle at the center. Is every circle have a center? That's for a circle with a center at the origin. Does every circle have its center at the origin? No. I wish it did, but it doesn't. So, how can we tweak that if the center of our circle is at a different point? So let's say the center of our circle is now at the point 5, comma, negative 18. What am I going to tweak to my x's? Sorry, it's at negative 5, comma, 18. I said 5, comma, 18. Negative 5, comma, 18. So what do you want to tweak now? Okay? So you want to go 30 cosine of t and then minus 5? I don't want to be back at the origin, though. That's the problem. Yeah. I want to be where the center actually is, right? Then minus 5? Yep. Okay. And what would my y one be then? 30 sine of t plus 18. Now, it's going to be very important that you make sure that those aren't inside with the t, so that they're separated and that t isn't that minus 5. It's not t minus 5 in parentheses. That tweaks everything. It's all crazy. Okay? What about if our center is at 0, comma 25? Still a radius of 30. Do I have to add anything else to that one? No? Okay. What about to this one? Plus 25. Which actually makes it pretty easy. Whatever the x part is, we move it 5 to the left, so we move it 5 to the left, subtract 5. Move it up and down, whatever it is, we just add that. Alright? Yep. We're on a Ferris wheel now. You ever been on a cool Ferris wheel? Go get a pass.
Sorry. My car's already split.
That's fine. That's fine. Just get a pass so that you make sure you checked in. Okay? Have you been on a cool Ferris wheel? Yeah? Which one? Yeah. Sea-Lot? Yeah. I was on one that went through the ceiling once. But it was, the ceiling head was cut out. It was at the X Center in Cleveland. They cut a little trench in the ceiling, popped it up, and so when you were riding it, you rode through, and then you got to look up, you got to see outside, you got to see the airport and the skyline of Cleveland and Lake Erie and all that stuff. And you went back down and you saw the inside, and you went back up. My idea for the best Ferris wheel goes underground. So you load it up at the top, and then it goes underground. And when you go underground, you go through an aquarium. $1 million idea sitting up here. Lots of them. Okay? Alright? So, we got a Ferris wheel with a radius of 30 feet. It's rotating counterclockwise at a rate of 1 revolution every 20 seconds. So I'm going to see if I can actually make this thing go all the way around. I have to hold the legs apart. This was somebody who did a circle project a couple of years ago. Okay? So it's going around, and it takes 20 seconds to get all the way around. Oh, there it was. See? Bad glue. Okay? 20 seconds all the way around. Okay? Bottom of the Ferris wheel is 10 feet off the ground. What position are you in 22 seconds into the ride? Okay? So let's get our first guess at said circle. Okay? What would the parametric equation be for this circle? I need an x of t, and I need a y of t. Radius. 30. Sine or cosine? Cosine. T? Yes? Anything else to add there? Nope, sounds good. Radius. 30. Sine or cosine? Sine. Of t? Anything else to add? What? Plus 10. If we add 10 to it, and our radius is 30, what's going to happen? What's going to happen? It's going to be underground. Are we underground? I hope not. I hope you never get on an underground Ferris wheel unless there's a trench cut in. You know what I mean? Okay? So we can't just add 10. Add 10, that's a no. Let's logically think about this. Here was 10. Here's my center. Here's 30. So what am I going to add to my center? 40, right? Okay. So 40. Love it. Graph me that circle on your calculator. I'm going to start a whole new page. So we said 30 cosine of t. We said 30 sine of t. Then plus. Front row, I don't see it. What do we got to do? Change my window, right? Okay. Now, let's be thinking about this window zooming, window settings type things. Left and right, how far out do I at least need to go to see it? Got to go out left and right 30, right? So let's go a little bit more than that, Let's go 40. So let's go negative 40 to positive 40. We can go by tens. I like to see the ground. We'll adjust that later. How high up does the Ferris wheel go? If you're sitting on the Ferris wheel, how high off the ground are you? 70, because it's 30 from the bottom, right, to the center, another 30 from the center to the top, plus you're 10 feet off the ground at the bottom. So that's 70. So I would go up to 80 there. Oops, tap the brakes, min. I'm going to go negative 10 to 80, also going by tens. What's wrong? Here's my Ferris wheel ride. Right there. What's wrong? We're in degrees. We need to be in radians. There's our Ferris wheel ride. Doesn't look very round, does it? Okay? That's just the distortion of the ratio of the screen that you're seeing. If you want to, if you have to, absolutely have to have your Ferris wheel be circular, you can go menu, you can go window zoom, and then you can scroll all the way down here to the bottom, and letter B says square. If you square up your viewing, then it takes it into a circle. But then it adjusts your window, and then you gotta kind of zoom out here a little bit, and then that's if you absolutely positively need to have it be square. Okay? So now, with that being said, let's trace here, but instead of tracing, I want to go trace step first. Trace step, and let's go with 1. I want to go with a whole single second as my trace step. Trace step 1, menu, trace, graph trace. So here we are at the start. You get in, the bar comes down. I don't even know if they have bars. Like the last couple of Ferris wheels that I rode, it's just been like the gondola ones where you're just sitting around in a circle. Okay? Okay? Here we go. Ready? 1 second in, there we are. 2 seconds in, there we are. 3 seconds in, we're over there. 4 seconds in, we're down there. 5 seconds in, we're down there. 6 seconds in, we're there. Wait a second. What's wrong? Only takes us 6 seconds to get all the way around? What did the problem say? 20 seconds to get all the way around, right? 1 revolution every 20 seconds. Ruh-roh. We got to make some adjustments. Okay? Now, I'm going to bring back some old math here now. Okay? Old school math told us that if we had a function, or y equals, we had a, we had either sine or cosine, we had bx plus, oops, not plus c, minus c, oops. Minus c, then plus d. Remember that? When we were graphing functions, what did a do for when we were graphing sine and cosine functions? A was the amplitude, right? A now for us is going to be the radius of your circle. Okay? A is going to be the radius of your circle. B is going to be the period still. Do you remember what the period was equal to way back, beginning of the semester, end of last semester, when we were graphing trig functions? What do you got, Chris? Close. there is an absolute value, and there is a pi. Period equals, anybody? Somebody just said it. 2 pi over b. Yeah, 2 pi over b. For terms of this one, Chris, we're going to forget the absolute value because we're always focused on the ride, not backwards. Yep. Yep. Okay. All right. C here is going to be where you load the ride. We'll talk about that here in a minute. And that's going to be your loading position. Straight out to the right is 0, so then there is no C. If you load at the top, it's minus pi over 2 inside there. If you load on the left side, it's minus pi. If you load at the bottom, it's minus 3 pi over 2. And so on and so forth. And D is going to be center off the ground. Okay, which that's why we went with plus 40 there. Okay, so let's figure out our period. Our period was 2 pi over b, which also means then that b is going to be 2 pi divided by the period. The period, we said way back at the beginning of the semester, was the amount of time it took us to make one complete wave. Yes? Or one trip around the circle. Yes? Well, we're dealing with a Ferris wheel that's going in circular motion, so the period, it'd be 1 revolution. In this case, it said we made 1 revolution every 20 seconds, so it's going to be 2 pi divided by 20. Can that be reduced? Pi over 10? Okay. So our new functions now that we've adjusted those, our new functions x of t is going to equal 30 cosine of pi over 10 t. Added the b value. Y of t is going to equal 30 sine pi over 10 t, then plus 40. The best part is, because we already inputted it, we don't have to go and redo a whole brand new one. We can just tweak the one that we have. So we're going to hit tab. And when I go up, that takes me to the function that I have right there. The only thing that I need to add is I need to add a pi over 10 in front of my t. Here is the easiest way to add that. Control divide puts a fraction in there. Control divide, and then you can put pi from down here on the pi key, or you can type the letters P and I, and it will happen. And then you need to fill in 10 underneath. You need to do that in both of those spots. Control divide adds the fraction. You can use the pi key, or you can type in the word pi and then 10 in both of those cases. Okay. When we hit enter, we should see a nice, beautiful Ferris wheel ride. Ruh-roh. What happened? How come it didn't go? How come we didn't get to go all the way around? How come we didn't get to go all the way around? Why? What's wrong with the T restriction? Nope, not that T restriction. How many seconds is this ride going? It's only going 6.28 seconds. How many seconds does it take to get all the way around? 20 seconds. So let's go with a number here bigger than 20. We need to get to 22, right? So let's go even bigger than 22. 25. Okay. Let's go 25 here. Now we have ourselves a Ferris wheel ride for the ages. Okay? So if we trace this thing, let's go back, let's restart. So there we are at 0. We're tracing. We're starting out, and that's where it said we're going to start. How long should it take us to get to the top? If it's 20 seconds all the way around, how long do you get to the top? 5 seconds? There we are at the top. Is that where we should be? Yeah. 70 feet off the air? Yep. Okay. 10 seconds gets me to the other side. 15 seconds gets me to the bottom. 20 seconds gets me back to the start. 2 more seconds puts me there. Okay? Here's another cool thing. Oops, let me go this way. Go this way. We're going around. We're going around and around and around and around. Okay? Wherever I'm at on this, I can just type in whatever seconds I want. So for instance, I want to be at 22 seconds. I can type in 22. As long as I'm in the trace, I can type in 22 and it takes me right there. Okay? So in terms of positioning, we are, or you are, 24.3 feet right and 57.6 feet off the ground. In terms of the question that we asked was, what is your position? Okay. Now, some tweaks that we can make on the same problem. It is so important for you to critically read these directions, or I shouldn't say these problems would be a better way of saying it, especially when we're dealing with circular motion. Because small little words make huge differences. Okay? The first little word that you need to look for is clockwise or counterclockwise. If it's going counterclockwise, everything's normal because the unit circle is set up counterclockwise. Okay? So no tweaks there if we're moving counterclockwise. If we're moving clockwise, that means we're going in the reverse direction, which means you need to have a negative B value. So a positive B value will move you counterclockwise. A negative B value will move you regular clockwise. Okay? Makes a difference. Another tweak that we can make is starting position. If we start at the top, well, then you're going to have something in the neighborhood of you're going to have your B value times T minus pi over 2. Or you could have your B value times T plus 3 pi over 2. Both mean the exact same thing. It all really depends on if you are a minus or you're a plus type of person. Okay? If we start at the bottom, it would look like that, or it would look like that. If it started at the left, then it would look like that. Plus or minus pi. Doesn't matter, because it's plus pi puts you on the left side, minus pi puts you on the left side. Okay? Or if we said some other angle, that Ferris wheel that I loaded in Cleveland, that I rode on in Cleveland, it actually had 3 loading spots. So it loaded 3 gondolas at a time. And they were like right here and here and here. So we could have loaded at 4 pi over 3. And then it would be minus 4 pi over 3. Or plus 2 pi over 3. Okay? All that fun stuff. Let's just get these parametric equations set up. In 2 minutes, I think we can get those set up. Okay? Ferris wheel with a radius of 60 feet. Period is 12 seconds. And the bottom of the wheel is 8 feet off the ground. It's rotating clockwise, and we start at the bottom. Okay? So we're starting down here. It's 8 feet off the ground. It's got a radius of 60 feet. And we're going clockwise. So that means we're going this way around. For sure, we're going to be 60 cosine. For sure, we're going to be 60 sine. Because that's our radius. B value comes from period, right? Okay? So period equals 2 pi over B, or B equals 2 pi over the period. My period was 12. 2 pi over 12 reduces to be pi over 6. But we're going clockwise, so it needs to be negative pi over 6. And I got T. And I got T. We're starting at the bottom. Minus 3 pi over 2. We're 8 feet off the ground at the bottom, right? So where's my center then? 68. So then it's plus 68 here. One last thing. Start at 0, and this number here has to be bigger than bigger than 12 to get around. Yep, bigger than 12. Thanks for staying a couple extra seconds. Tomorrow you have a formative.